All right, guys. Today we're going to move into showing how sound is simple harmonic motion and how the motion of a spring and pendulum can actually mimic sound waves, or we use that to explain sound waves. So let us get into this. And first we're going to talk about simple harmonic motion. This is going to be section 2 in the chapter, but I'm going to start with this first. Simple harmonic motion is basically a motion that repeats itself as it goes, as something, a bob or a spring goes back and forth. So we're talking about something swinging back and forth. And this is basically called simple harmonic motion because 1 is a simple motion and 2 is in harmony. It goes back and forth, and the period of time stays the same as it goes back and forth through its cycle. And what we're going to use, to look at some harmonic motion, we're going to look at spring and a pendulum. And this is what we're going to use to start this topic. And we're going to use that to explain wavelengths of sound next week. And note that for spring, elastic force is opposite of displacement. And then at the maximum displacement, we're going to talk the velocity is 0. And then, so what happens is the springs go up, or the pendulum, as it's going up to the very top of its swing, the velocity, when it reaches there, the velocity is 0. Same thing with the mass. If we take a mass on a spring and we vibrate the mass, as the mass gets to the bottom of where the spring stops, its velocity is 0 because then it's going to go back. At equilibrium, the force is actually 0, and the magnitude of the velocity is maximum. Not 0. Whoops, sorry, there's a typo. I looked at that. I thought I'd double check this, but this is at maximum. So as pendulum goes from here to here, this is the equilibrium point. Force acting on this is 0, but the velocity is at its maximum, whatever that velocity may be. So when we look at simple harmonic motion, we have 3 things: amplitude, period, and frequency. I'm going to relate this to sound waves in the next lecture. But the amplitude is the displacement from equilibrium. And if we're looking at a pendulum, it would either be radians or angle, or the angle of displacement. But when we're talking about a spring, we use meter, because that's how far it goes. Now the period is the time it takes to go from one end to the other and back. So what we mean by this is, if this is where we begin at this point, it's going to the right. So the pendulum goes through the center to this point and swings back. Once it begins to go back to the right again, we call it, that's the end of the period. That's the time it takes to go what we call one full cycle. And the frequency is just the inverse of the period. It just tells me how many number of vibrations we have per second or per unit of time. And it is per second. Now, I want you to realize when we talk about hertz, we actually talk about seconds to the minus 1 and 1 over seconds. We'll always use this type of notation. And so this is going to be very important for us when we talk about springs and simple harmonic motion and actually pendulums. So let's look at Hooke's law. This is what we figured out with springs. And the force involved with Hooke's law is equal to minus kx, where k is the spring constant and x is the displacement from 0. Now, when we talk about this, here's our spring. If we have it from the ceiling, it's got nothing on it. This length from here to here is the length of the spring, and it's going to call this point the 0 point. So if we stretch it out a little bit, this x is going to be our displacement. So this is my displacement. However far we pull the spring or compress it. Direction and sign, again, is based on our point of view. In this case, this is minus x. If we compress it up to here, this is going to be positive x. If the spring is attached to something horizontal, this is positive x and this is negative x. It all depends on your point of view. And this is going to be key. So here's our mass spring system. Now I want to point out that the elastic force, the restorative force, because it's the force that restores it back to equilibrium, it's going to be opposite of the direction that it goes. So elastic force is equal to the negative mass times acceleration, or negative spring constant times the distance it displaced. So the elastic force is equal to, this is Hooke's law, minus the spring constant times x, because it's in the opposite direction. So at this point, it's not moving. It wants to move to 0. So here's the elastic force. As it goes past where the equilibrium point is, there's no more elastic force. All of it's converted to kinetic energy, which is moving this way. And then at maximum displacement, there's no more kinetic energy. It's all potential, which is this elastic force. And here's the distance, minus x. Again, it's opposite direction of the elastic force. So x is opposite of the elastic force. And that's something we need to remember. Now, when we look at a pendulum, it's going to be very similar to a spring. Now, we have a string and a bob. Bob is the mass at the end of the string. And this is basically when we talk about pendulum, if I can spell string right. And the weight of the bob is going to be the part of that restoring force of the pendulum, because so the mass of the pendulum is a part of this. So we have the string, and here's the mass. Now the distance, the mass, helps restore the force. The length is actually a very important part of this as well. So when we relate simple harmonic motion with the spring, here's our displacement. We use the angle from the center for our displacement in a pendulum. Where actuality in the spring is actually the distance away. It moves back and forth, and this is what we call simple harmonic motion. And this is what we're going to talk about this chapter related to sound for my next lecture. If you have any questions, please let me know. Have a good day.